Okay, so we're moving on to chapter 2, which is called derivatives. Now, what we've been doing has been basically derivatives at a very basic approach. So the derivative of a function is the instantaneous rate of change of the function at a specific value of x. Instead of writing ERC of f of x at x equal to a anymore, we're now going to write f prime, so this little dash here is called a prime, of a, so that means the derivative of f of x at a, at x equal to a, or df divided by dx, so it's not really divided by a sign, but it's df by dx. This means evaluate at x equal to a. It's called a bar. Okay, we're mostly going to use this because it's a lot less writing. Okay, so for example, so now f prime of a instead of ERC is equal to the limit as h goes to 0 of f of a plus h minus f of a all over h. So the same formula, we're just now calling it f prime of a. Using a function notation, f relates it to the original function, the prime says it's something else, and then we're evaluating at a. Okay, so an example, let's try it with this function here. F of x equals x squared minus 2x. So f of x equals x squared minus 2x. Sub it into this formula here, and we're going to check that at x equal to 3. So at x equal to 3. Okay. So the limit as h approaches 0 of this is equivalent to this. Okay, so we've done this already with quadratics, so this shouldn't be a surprise. Okay, so we're substituting it in, simplifying that expression, and we've got this. Okay, so maybe what you want to do now is just pause the video and finish this off, see if you get it right. Okay, so do the canceling out, and we get down to this piece here, and now we can take the limit as h approaches 0 of 4 plus h, and that equals 4. Okay, so now we've just worked with this new notation. We're calling it the derivative, and we're doing this exact same thing we did before. We're going to take it a few more steps though. Okay, so this method here of finding the derivative is called find the derivative from first principles. So if you ever ask that on a test or a quiz, from first principles means using the limit definition of the derivative. Okay, so things are going to get really nice here after a little bit, but it's going to require a lot of ugly hard work first to get to a really nice point. Okay, so the derivative of a function, that is, leave x as a variable, is this. Okay, so f prime at x, so we're not actually going to sub in a number now. We're not going to call it a, we're just going to leave it as x. So this is going to give us a new function where the variable is x, and it's related to the original one where it's the instantaneous rate of change of that function at any value x. Okay, so the same value as x. Okay, so let's try it for this function that we just did at 3. Now we're going to just leave it as x. Okay, so we've substituted into that formula. We're expanding now. We're not substituting a value in for x. We've seen this before with just value of a, so now we're just using x. Okay, things cancel out, the x squareds minus 2x, and you're left with an expression on the top with an h in it, each term, so we can cancel that h out on the bottom, and now we've got something where we can take the limit of nicely. Okay, so you might want to pause the video, go back to the original, and try to do this on your own without looking. Okay. Now, we can say that the limit of that, get rid of the h, is 2x minus 2. So the derivative, or the instantaneous rate of change, or the slope of the tangent of f of x at any value x is 2x minus 2. So if I want to find the derivative at x equal to 7, I just sub in 7 here. At x equal to 35, I sub in 35. At x equal to 1,000,004, I plug in 1,000,004. And that'll tell me the instantaneous rate of change of that function at those values. Okay, so this function can be used to determine the slope of the tangent to f of x at any x. Okay, if you want, you can check to see if this is correct. So you know that we did it originally. At 3 we did this, and we got 4. Okay, so if you want to test out your formula at x equal to 3, sub it into our expression. Well, 2 times 3 is 6, minus 2 is 4. It works. Okay, so same as the first example. Now, there is a whole list of ones that I want you to work on here. So the first list is a constant, x, x squared, x cubed, and then come up with a formula for x to the n based on the pattern you might see here. So you're going to use the same process called first principles, taking the derivative, okay, of each one of these to see what you get. Okay, so let's take a look at those ones. So maybe you've paused and tried this now. Okay, so we're going to look at the first one. So this is a, where it was just a constant. Okay, so we're looking at f of x equal to c. So in that case, f of x plus h, doesn't matter what you plug in, you're going to get a constant. F of x, constant. Okay, you see this? No matter what you plug in for x, you're going to get c. And then divided by h. So 0 over h is just 0. And the limit as h goes to 0 is 0. Okay, so the instantaneous rate of change of a constant is 0. And that should make sense, because a constant function, f of x equal to, say, 7, is a horizontal line that goes through 7 on the y-axis. The slope of that line is 0. So the instantaneous rate of change should be 0. Okay, the next one, where it's x, well, we'd go through the same process here, and we get 1. Okay, well, that should make sense too, because if you look at y equals x, that has a slope of 1. So the instantaneous rate of change at any point on there should be 1. So that makes sense. C for x squared. We've done this before. We go through, we get 2x. Okay. X cubed, we've looked at this one already. Okay, so we go through and we get 3x squared. So from this, you might be able to see a pattern. And hopefully you've seen the pattern where it's take the power down in front, multiply it by x, and reduce the power by 1. So for example, x squared, bring the power down in front, 2x, reduce the power by 1, which is that, and that's what we had for x squared. Okay, x cubed, bring the power down in front, 3x, and reduce the power by 1, so it's 3x squared, which is what we had here. Okay, you have to make a prediction for f of x equal to x to the 7. Well, then the derivative f primed of x would equal 7x to the 6. Okay, so that's a nice pattern for that one. So that's those ones. Now the next ones here, I'm going to flash them by here. So these are the rational ones. F of x equals 1 over x squared, 1 over x cubed, and then try to predict what it would look like for 1 over x to the n. Okay, so these ones, well, I'm just going to flash them here so you can try them and then check your answers. Here's the solutions for each one. They get a little bit messy after a little bit. Okay, so that's for f, that's for 1 over x. This one is for 1 over x squared. Gives you this nice answer. Okay, so try it, check your answer. And then this one is for 1 over x cubed. Okay, so 1 over x cubed. Expand that out, get a common denominator. It can get ugly, but it works out. Okay, you get this, which is negative 3x to the negative 4. And then from that, hopefully you saw the pattern of this. The You got negative n over x to the n plus 1, or negative n x to the negative n plus 1. Okay, so for this example, if it's 1 over x to the 7, say, then the derivative, so if that's f of x, then f primed of x would equal negative 7x to the negative 8, or negative 7 over x to the 8. Okay, so that would follow that pattern. And the next one, next group, is these ones, these square root, cube root, fourth root, nth root. These get very ugly. For this one, using a difference of squares, multiplying by the conjugate, multiplying by what you'd call a conjugate, I guess, of a difference of cubes, and then difference of fourths. Okay, so let's take a look at these ones. Okay, so here's the square root one, which again, we have seen this before. Okay, multiply top and bottom by the conjugate, and simplify till we get this. Now this is for this is for the cube root. Okay, in order to do that, we need to know this formula again, the difference of cubes. Okay, so we need to multiply these two things together here to get that. Or if you do x minus y, everything's cube rooted in this formula then. Okay, so that would be the same formula. Okay, or x plus h minus x, that's what it would look like. Okay, so you might want to justify that. So that's going to be used here. And this is the process for finding the derivative of cube root of x from first principles. Okay, so this is what you get. Then you have to multiply it by something so that you end up with this nice expression on the top. So this multiplied by this gives us this nice thing on top because of our difference of cubes formula. Okay. And at this point we can cancel out the h, x's, and we take the limit of that and we get this nice expression here. Okay. Do the same thing for difference of fourths. There is a formula for that, so you can verify this using long division. You go x to the fourth minus y to the fourth divided by x minus y, and you'll get this expression. Okay, making that substitution instead of x to the fourth minus y to the fourth, making it x minus y. You just fourth root everything. And then this is the one that we had specifically used in our expression. We want x plus h minus x. We want to get that, so the x's cancel out. We have an h on the top. Well, this is the expression you'd use here. Okay, so you can try that now knowing this. When you do try it, this is the ugly mess that you would end up with. Okay, so this mess is not pretty, but it works. And it works very nicely each time you go to the next level. Okay, so the fifth root, sixth root, and so on. It gets messier, but it works. Okay, and eventually you end up with this as the derivative of the fourth root of x. Okay, so fourth root of x is the same as x to 1/4. So hopefully you see a pattern in this. Basically you bring the 1/4 down and reduce the power by 1. So 1/4 minus 1 is negative 3/4. Okay, so the overall pattern you should see in this. Okay, and the whole thing is, no matter what the power is, if it's an integer, negative, or positive, or a fraction, a rational number, or a real number, any irrational number, this formula is going to work. And you should check it with any of the ones that we've just done.